Hi everyone, and I think a big majority of you already know who I am. So I will today talk about something that many of you actually listen to, but this time I will also give a little bit of a background information because I have more time. Just to make sure that we're all on the same page in terms of the theoretical background, and then I will share some of the results that I already have for my studies. So I included this section just to have a very quick introduction to X-ray binaries. We have usually neutron stars or black holes in the center, and then these systems are usually visible in X-rays and as well as the UV, infrared, optical radio, and even gamma rays in many cases. And we have the main powering mechanism as accretion. When you divide these X-ray binaries into two categories, you have high mass X-ray binaries and then low mass X-ray binaries, which is usually defined by the main donor star. And then these systems are usually characterized with Roche slope overflow or stellar winds as the main powering mechanism. I also have a little bit of sketching around to show, I mean, you can actually see it, to define the components of a black hole X-ray binary. We have the accretion disk, which is going to be the main topic of my talk today. As we know, we have the event horizon. We also have the corona structure, which is kind of just low density cloud of high energy electrons. We also have the relativistic jet, and in many cases we also observe the accretion disk wind due to many of the powering mechanisms. But for the main topic, I will be only talking about modeling of the corona and the accretion disk in general. So and also relativistic jets are usually observed in radio, which is not really covered in my energy range. Hello? Okay. So what can we do with the X-ray spectroscopy? We can actually use it as a way to kind of dissect these components and try to model them and maybe get some sort of an information about the black hole structure, the space-time around the black hole, and anything you can actually think about to describe these systems. So the main components are the disk emission. I'm sorry, you cannot really see it that way. So the main components is the disk emission, you can see, which is modeled in a very small region here. And then the coronal emission is actually happening through disk photons being Compton inverse scattered to higher energies, which you can follow over here, which is like, as you can see, in the high energies is the dominating part. You also have this relativistic reflection, which happens due to the coronal emission being reflecting off of the accretion disk, which is usually called the illumination of the accretion disk as well, which can be characterized by the Compton hump you can see here. So when you are actually like modeling the hard X-ray band, which is like basically these two components, you also have distant reflection, which is not really affected by the relativistic effects due to the gravitational potentials around the black hole. This is kind of a little harder to model, but still it's present. There's also another component that is not included here, which happens due to the light banding around the black hole, which is called it's again modeled through the reflection component, but it's basically disk emission being bent over here and then reflecting off of the accretion disk again. Oh. So the main, like the biggest image is that these systems are very variable. They go through so many accretion states, and they have tons of outbursts observed so far. So the main characteristics of these evolution is that you can actually track it in a hardness intensity diagram. In the x-axis is the hardness, which kind of defines how energetic or less energetic your spectrum is. So you saw the high part of the high energies. If your spectrum is dominated by the coronal emission and less disk emission, it means that your spectrum is hard, which can be seen on the picture on your right, which defines the low hard state, which is the beginning and the end of the outburst. And then your source starts to evolve around this Q diagram. And on the sides, you can kind of see the evolution of the accretion disk in relations to the relativistic jets. There's this line in the middle that's called the jet line, which kind of tells you at what state you can observe the relativistic jet or you cannot observe it. So as you go and start to have a little bit more X-ray, even the UV emission, you are transitioning through the intermediate state or the very high state, which is also divided into two, depending on how hard or soft your spectrum is. And then you start to evolve to the hard state, which is basically this sketch. It's a very simplistic sketch, but still a very good representative of how the accretion disk looks like. So the high soft state is actually where you have a spectrum that is highly dominated by the accretion disk, which is usually like the coronal emission is very low, and then you have a very high soft spectra. And just to give you an example of how these spectra compare, it's not a black hole X-ray binary, it's actually a neutron star X-ray binary, but still it is a very good comparison of how these two states look like in the spectra. So you have, oops, I'm still trying to use the pointer. So you have a hard tail over on the hard state, and the soft one is highly dominated by this by the disk. Come on. Okay, so one of the biggest global studies of accretion disks in black hole X-ray binaries was carried by Dunn et al. 2010 and 2011. So these two figures are very important for the rest of the presentation for two different reasons. So this blue line shows you the expected disk luminosity versus disk temperature relationship, and this group carried out the investigation by modeling these accretion disk spectra with a simple non-relativistic accretion disk plus a very simplistic power law component. They observed these weird deviations at the very high end of the relationship and at the very low end of the relationship. And when you actually look at the inner edge of the accretion disk versus disk temperature, you also have that kind of deviation in both ends. So it seems like there's some sort of a thing happening that they could not really explain. They only introduced some explanations, which I will also be talking about in the remaining parts of the slides, that these are deviating here. It can be model dependent. It can also be limited by RXTE's very small energy window, which does not really correspond to emission by the accretion disk, or it can be just completely depending on the model. So these two pictures are also going to be compared in the future. So I will shortly describe the spectral analysis process because it's not really that interesting actually, but I want to introduce the two models that I used. So the main goal was to see if the relativistic modeling of the accretion disk can actually have a solution to these deviations we saw on that specific plot. So in the non-relativistic disk model, I'm sure some of you are actually familiar with this. It's the disk BB model. It's a very simplistic Shakura-Sunyaev disk, and it only has two parameters, the disk temperature and then the normalization, which can be also interpreted as the inner edge of the accretion disk, if you know the inclination angle well. And then we also have two relativistic disk models. KYMBB was developed by Michal Dovček in Prague, and we also have KARBB. These two models are essentially the same. Okay. I don't know what's happening, or no? That's not really. I didn't know.
I think you just woke up.
I think it's okay now.
Yeah, it just, I don't know. It just woke up and like started doing things.
So the two models are actually employing the ray tracing method to calculate the spectrum emitted from the accretion disk around the black hole, and then it basically calculates the traces how the emission is actually reaching the telescope. So both of the models have black hole spin, black hole mass, and inclination angle and distance as common parameters. The main difference between these two models is a very simple and very important parameter, that is how you define the Rin. So in this sense, Rin is usually defined for at least the Novikov-Thorne model, is that we always assume that the accretion disk is extending down to R-ISCO. With KYMBB, you can actually have it as a free parameter, and you can investigate how Rin is changing throughout the entire outburst. That's why we are using and actually comparing these two models. So, how does the accretion disk in GRO J1655 and -40 evolve? So this was the picture I showed you before. What we did was try to reproduce the same data set and the same plots and see if we can actually... One of the things that I changed in this too is to have a better solution to the instrumental uncertainties, because RXT is not really well calibrated instrument. It's a very old instrument, so it's subject to very high instrumental uncertainties. So we had the same model in both these two cases, and we can kind of see that the deviations are still there. These did not happen here, mainly because I had to exclude those due to some unconstrained parameters. So I have a better set of spectra, but many parameters are not well constrained, so they're not really presented there. I will just continue. And then in the middle, I replaced this BB with CARE-BB to see actually we can do anything with modeling it relativistically, but we did not really see any difference. The main difference happened when I let KYMBB with a variable Rin parameter. So what we could see was that we observed much more variability in the points, but it's mostly because it has a huge variety of parameters, and some of them are degenerate between one another. So that can explain the more scatter, but we could definitely see these points to be pushed back towards the relationship that you are expecting to observe. So how does the evolution actually looks like? We have this non-relativistic evolution, which corresponds to very low Rin values, which is kind of already like expected, because you have you are assuming a very perfect black body emission. That's what this BB is doing. But there are a lot of processes that happen around the black hole and within the accretion disk atmosphere. I will talk about them in a very short period of time. So it does not include any of the modelings of these things. So it's kind of logical that it's very low. But the main problem with these is that they are actually quite lower than the R-ISCO values when you calculate them for specific spin values. For GRO J1655-40, it's usually expected to be around 0.7, and if you look at it, it's always below R-ISCO. And this is not the region that you are expecting to have any emission from. So when you replace disk BB and CARE-BB and look at the spin evolution, it kind of looks like quite reversed, which is what you expect. But the problem is that you are not really expecting to have a changing spin for a black hole. The only thing happening here is the problem is that it's assuming that it's always at R-ISCO, so it's always calculating the spin as if it's at R-ISCO. So you can actually interpret that as changing at R-ISCO, but that's also not what you're looking for. So what you can actually interpret this as a changing Rin, which limits how well you can model your inner edge, which also limits how well you can actually measure the spin using CARE-BB. So if you want to take a look at how disk BB versus KYMBB compares, now you have quite a bit of a fixture to the values that you are having for Rin. All of the values are above R-ISCO now, and all of the temperatures are at least 50% lower this way. I will explain why exactly that is happening. I just want to quickly show how these two specific sources actually compare. I did not really include all of these luminosities for LMC X3 because they did not observe the same deviations. I also did not observe the same deviations in the luminosity versus disk temperature diagram. But the comparison was important for these two sources because this is a mostly stable, almost always on kind of source. You can kind of see that the Rin is not changing that much. So it was important to actually test these two models and KRBB and KYMBB to see if changing Rin was quite important. So the change in the values are quite consistent, but there was a bit of a problem due to because LMC X3 is much further out compared to GRO J1655, so the spectral quality is a little worse, and KYMBB is not really a friendly model when it comes to bad quality spectra. Now, I want to talk about what exactly needs to be changed and why we cannot use disk BB. So this spectral hardening is usually used to explain all of the deviations in the effective temperature of the accretion disk due to the presence of accretion disk atmosphere on top of the accretion disk. So it's not really, in reality, it's not a slate. So we already know from the puffy disk structure, it cannot be just a slate, a clean cut of material. So we cannot do that. Now, what happens? So this is your observed X-ray spectrum, but your disk BB model assumes that this is your effective temperature, and it assumes that you are always observing that effective temperature at specific radii. So it's a multicolor disk black body spectra. So it's like summing perfect black body emissions at different radii. But this is not the case. You have a lot of upscatterings happening in the accretion disk atmosphere, which happens to start to dominate over any of the observed processes when your accretion disk temperature, effective accretion disk temperatures, is reaching around 1 keV. So if your accretion disk is starting to evolve towards the accretion, towards the black hole, you're going to end up with much hotter accretion disks. So your accretion disk atmosphere is also going to heat up. So what's going to happen is that the radiation emitted from the surface is going to be upscattered to higher energies, and that's what you're going to be observing, which is called the color temperature. And then this specific parameter is also called the color correction factor. So that's the main reason that we're observing much less disk temperatures with relativistic accretion disk models, because these two models and some non-relativistic models have this color correction factor as a parameter. Generally it's at 1.7, but it's usually assumed to be variable throughout the outburst, because if your accretion disk temperature is changing, then you're also expecting to have a change in the color correction factor. Can we actually do that? So what we did with GRO J1655 was to see if we can actually observe this change. One teeny tiny problem is that both KYMBB and KRBB are not really devised to be able to model that kind of a change, because it strongly depends on the mass accretion rate, accretion disk temperature, and also spin of the black hole. So if you have all of these parameters as free parameters in your model, and if you want to look at them, and then you end up with a free color correction factor, it's quite degenerate, so whatever you are having is not really that reliable. But if you can, constrain these parameters a little bit more, and you can actually look at a very rough evolution of this parameter, which we found to be changing between 1 to 2.2, where the 2.2 happens to be in the high salt state, and then you have 1 in the low hard state. The main difference here is that it makes sense this way if you look at the physics behind this parameter, but this was not observed in the previous studies with different models. So this is one of the new things. One thing people suggested was that this change in color, this color correction factor can actually be replaced by the truncated disk radius. So if you are seeing an evolution in the disk temperature, people actually think like instead of actually changing inner disk radius, the disk is always there, the disk is always extending to our ISCO, but it's kind of the thing that is changing is the accretion disk atmosphere. It's kind of impossible to test this theory with the models that we have right now, so it's still a big question mark. As I said, there's a strong degeneracy between the black hole spin and the color correction factor, so it's still not really that reliable to define, okay, I can measure this color correction factor from this specific observation and then I will say it, okay, it's 1.9. When we tried to have this color correction factor as a free parameter and we tested the deviations that I showed you before, we did not see any of the fixtures that we observed with KYMBB where we had the relativistic disk modeling, but we also allowed the inner edge of the accretion disk change. Because as you also know, the effects of the relativity or general relativistic effects are strongly dependent on how close you are to the black hole or to any compact object. So it's a very important relationship together when you think about it. Okay, I am coming to the summary. It's like we already know that the black hole X-ray binaries are very nice, very ideal environments to study the effects of the general relativistic effects on the observed light. This is also one of the ways to actually do it with X-ray spectroscopy. The other options are studying the polarimetry. This is not really my job to do. We kind of see that there's a very strong significance to the accretion disk properly. So I only did a very simplistic comparison of Novikov-Thorne versus Shakura-Suniev disk modeling, but we know that the disk structure can be very different. There are many different ways of describing the interchange in the hard and soft components. But one of the biggest takeaways is should we really rely on defining our in at our ISCO all the time when we want to measure the spin, because there is even like a big variance even in the high soft state. If we still assume that way, then we are in a big problem. As I told you before, changing color correction factor or the spectral hardening cannot really explain any of the deviations that I presented you, and there's also 50% difference which cannot be explained by only color correction factor, because if you apply 1.7 color correction factor, the change is supposed to be around 70% if you include a little bit of uncertainties, but 50% is not really within acceptable uncertainties. And the truncated disk scenario, when you combine it with relativistic treatment of the accretion disk, can actually provide a very nice fixing to the observed deviations in luminosity versus disk temperature. And I would like to leave you with the same picture. This is how I think the accretion disks are actually forming. Thank you.